Okay. Hi everyone, it's a pleasure to be here in this symposium. My name is Miguel Marten. I'm presenting our study in nonlinear displacement model in regional reference frame, a case study of the REDGEOMIN Chile and SIRGAS network in collaboration with my colleagues from the University of Santiago, Chile, and the National Geology and Mining Service from Chile too, or SIRGAS-CON in Spanish. Today I will cover our methods, results, and the implications of our case study on the mentioned GNSS networks, and let's begin. First, let's set the context. The Pacific Rings of Fire is a focal point for geoscience due to the great dynamism in the area, manifested through the occurrence of earthquakes and abundant volcanic activity. Both the SIRGAS network and the REDGEOMIN network, located in Chile, are situated in one of the most seismic regions in the world. This high level of seismic activity poses fundamental challenges for the kinematic of geodetic reference frames, which can show significant variations due to large magnitude earthquakes. Our study addresses the kinematic of geodetic reference frames in a highly seismic region. Seismic activity significantly impacts precise geodetic measurements. Accurate modeling of this variation is crucial for understanding and applications. Accurate models of this variation is crucial for understanding and application. These issues is evident in GNSS time series worldwide. For example, two REF stations here in Switzerland, SIM2 and WAC2, and two REDGEOMIN stations in Chile, CGTC and FUTF, show clear behavioral difference, mainly due to large earthquakes. Here we have a closer look at the WAC2 time series, a station located right here in Bern. In approximately 20 years of data, we notice practical linear behaviors in time series. In contrast, at the CGTC station, located in northern of Chile, the occurrence of a large earthquake in 2014 is clearly observed. This is why our objective is to characterize the deformation patterns using GNSS data for seismic and non-seismic events. We model nonlinear displacement in REDGEOMIN and SIRGAS networks and analyze the events affecting this displacement. We compare the OREF and SIRGAS network, black triangles, with earthquakes over magnitude 6.5 since 2000, red dots. And notably, the OREF map shows 18 significant earthquakes, but the SIRGAS has 245 events in the same period. To achieve our objectives, working methodology is necessary. We collect data from the SIRGAS and REDGEOMIN GNSS networks. REDGEOMIN data is processed at the Geodetic Processing Analyzing Center using the IGS products for wiki solutions. From SIRGAS uses Repro2 weekly solutions. We update all available GNSS stations and apply a nonlinear displacement model for significant seismic events with millimeter level accuracy. Machine learning tools cluster a station based on deformation patterns, optimizing the number of clusters for best results. The displacement model for the GNSS time series is shown on the screen. It's considered three main aspects. First, secular motion, instrument-related variations, failures, antenna changes, etc. And seasonal oscillations, mainly due to surface weather low changes. Earthquakes associated deformations appear as abrupt jumps with a heaviside function, co-seismic, and post-seismic deformation is modeled with the logarithm and/or exponential function. We use the K-means algorithm to cluster stations based on deformation patterns and locations. These data are processed and entered into the K-means algorithm, then tested with the analyzed deformation beyond Los Andes, or ADELA. This model calculates the position of a point at the specific epoch by modeling the time series of selected stations. We compare this position with observed coordinates to verify the population accuracy. Traditionally, the ADELA model selected the 4 nearest stations to the point of interest, left map, and using the K-means algorithm, we now select stations within the same cluster as the point of interest, such a cluster in the northern Chile, right map. With this methodology, let's discuss the results. We present results from the SIRGAS and REDGEOMIN networks. The figure shows a histogram with normalized frequency of a residual obtained as the difference between observed GNSS data from each station in the network and the model fitted to each time series. The root mean square error indicating millimetric precision is 2, 2, and 6 millimeter in east, north, and vertical direction. Next, we showcase the AREC stations in southern Peru, which recorded 5 seismic events with magnitude greater than 7 during the observation period. On the right, the residuals for this station show values the 1, 1, and 2 millimeters in his components. Finally, the image shows secular velocities for each station, illustrating the formation patterns within the SIRGAS network. These patterns align well with the complex tectonic context and various plates boundaries in the region. For REDGEOMIN, we conduct a similar analysis, finding residuals in this network at millimetric values of 2, 2, and 6 in his components. As another example, we consider the QTAY station in central Chile, which experienced a magnitude 6.9 earthquake in 2017. These residuals for this station are 1, 2, and 4 millimeters in his components. Finally, observed velocity in this region revealed differential behaviors between northern, central, and southern zone of Chile, influenced by the interaction of Nazca and South American plates, and 3 large earthquakes in recent decades. Image below depict annual displacement changes from 2019 and 2022, showing homogeneous behaviors in direction and magnitude of displacement vectors in the northern zone. In contrast, the central zone shows a complex behavior influenced by the post-seismic process from 2 large earthquakes, the 2010 earthquakes with magnitude 8.8 and 2015 earthquake with magnitude 8.4. Finally, in the southern zone of Chile, the behaviors becomes quite homogeneous again, with much smaller magnitudes, mainly associated with the lower convergence rate between the Antarctic and South American plates. Let's analyze and interpret our results, starting with deformation rates. We focused on accurately fitting GNSS time series to enhance our understanding of surface deformation, crucial in regions with complex tectonic context. Accurate modeling reveals how surface evolve over time under geological stresses. Next, we examine behavioral differentiation, observing how the specific areas are affected by significant seismic events. Both REDGEOMIN and SIRGAS networks show deformation patterns influenced by seismic activity and large earthquakes. Identifying these patterns helps us understand seismic impact and improve our models. Now, let's discuss the practical implications of our study. Firstly, by accurately feeding GNSS time series and analyzes deformation patterns, we improve precision in regional reference frames. This enhanced precision significantly impacts GNSS data analysis, updating geodetic reference system for increased accuracy and reliability. The map illustrates the station clustering using the K-means algorithm based on strength variables, particularly in areas affected by recent large earthquakes in central Chile. Adjacent to the map, a table displays a statistical precision of coordinate calculations, comparing traditional method with cluster-based approaches. We observed millimetric improvements in precision and reduced variability. And finally, we will present the products developed by the Geodetic Processing and Analysis Center based on our findings and other research. As a center, we have access to the coordinates of the time series. If you scan the QR code on the slide, you will find a website. It's still under construction. And this site will soon feature our Avela model coordinate calculator, additionally based in our time series modeling results. We are testing PSD files for future use in Bernese. Moreover, we have contributed to the geoscientific community with 2 articles, one already published and the other in process, to enhance the understanding of geoscience. In summary, our findings highlight the need for the kinematic reference frames in continental Chile due to significant surface deformation from seismic activity. Nonlinear modeling of GNSS time series is essential in regions like SIRGAS and REDGEOMIN, given their complex geodynamic and high seismic activity. For future works, we plan to fully utilize machine learning tools, incorporating information on active fault system and diverse geological contexts. We aim to apply clustering techniques to identify areas with similar deformations, patterns, and analyze their evolution over time. And that is all. Thank you for your attention, and sorry for the time.